concentrated in a single point. Now, when I speak about point, this does not mean that it is strictly a mathematical point. It may have been a small volume. But just for simplicity, we can describe this as a point. Even that it may have been a physical point, not necessarily a mathematical point without dimensions and so on. So from Hubble's law, it follows that some times ago, all the matter in the universe was concentrated in a very single volume. And that was in fact the moment when the entire evolution of the universe started. And this model, which is based on this idea, so the expansion of the universe from a single point is known today as the Big Bang. So today the dominant model in cosmology is the Big Bang model, which assumes that in fact everything, all the matter existing in the universe originated from a single point and after that expanded from this point. Now the idea of the Big Bang was very controversial for a very long time, for around 40 years. But one of the main evidences for the Big Bang model came in 1965, where two engineers called Penzias and Wilson discovered the so-called cosmic microwave background radiation, which is one of the most important evidences for the Big Bang. Now, probably you know the history of this discovery. Penzias and Wilson were in fact two engineers who worked for the Bell Labs, and their goal was to build some kind of antenna on some frequency. And they built the antenna, which is probably this one. And when they tried to use it for communications, they have found out that there is some noise. So it was always a signal, and they could not eliminate that signal, whatever they have tried. And then one of these scientists or both met another scientist, Dickey, was a professor at Princeton, and they told him about this situation, and Dickey and some others previously immediately realized that this should be the noise, should be in fact of a noise of a cosmic origin. It should be in fact the signal due to the presence of some radiation, and this radiation today is known to be a remnant of the so-called Big Bang. Because initially the universe was very hot and dense, the photons and the baryons form a plasma, and because of the plasma, the matter and the radiation at some moment decoupled, that this kind of radiation should have survived, and today we measure it as the so-called cosmic microwave background radiation. And this cosmic microwave background radiation, it was initially very hot, but because of the expansion of the universe, it cooled down very much, and today it has a temperature of 2.7 Kelvins. Okay, what this radiation has an almost perfect black body spectrum. So what is a black body? A black body is a theoretical body which either absorbs all incident radiation or emits all possible radiation. Now this black body was thought to be a theoretical abstraction, because on Earth it is impossible to construct a perfect black body. But the spectrum of the cosmic microwave background radiation is an almost perfect black body. It's better than any black body that can be constructed in the lab of Earth. So this spectrum of the CMB is a black body spectrum. Now, it has also a very important property. First of all, this is extremely isotropic. The spectrum of the black body radiation is extremely isotropic. What it means? means that the intensity of the radiation coming from that direction is equal to the intensity coming from that direction, and so on. So the radiation coming to us from all directions has the same intensity. This means that this radiation is very isotropic. The isotropy of this radiation has a very important implications. It shows that the universe itself is also very homogeneous and isotropic. The universe is very homogeneous and isotropic. However, there are some small anisotropies in this spectrum. What is their physical origin? So since the photons traveled to us from the Big Bang, or very close to the Big Bang, so there is an imprint of all the physical processes through this photon went on. So these photons interacted with the galaxies, interacted with all kinds of matter, and there is an imprint of all these physical processes. And these physical processes, in fact, they generate a small amount of anisotropy, which is of order of 10 to the power minus 5. It is a rather small anisotropy, but it is extremely important because it tells us the entire history of the travel of the photon. And by this it tells us a lot about the history of the universe and about the interactions that photon has undergone. So, first of all, as I have already mentioned, it is the isotropy of the CMB is important because it indicates to us that the universe is also isotropic at the large scale. And of course, it can provide important information about the origin of the density fluctuations, interactions of the photon in the matter, etc., which and gives us a very good information about the basic physics of the universe. Now, these are the most important facts in cosmology. Cosmology as a science is based, in fact, on two major results. And this is the expansion of the universe and the cosmic microwave background radiation. There are many more other informations, but these are the most important, the basic and the fundamental observational aspects of cosmology. Now, in order to understand theoretically these results, we need a physical model, a physical theory to interpret all these observations. And this physical theory turned to be the theory of the relativity, which I will briefly describe to you. I apologize if my description is very simple. Probably it's too simple for you, but anyway, apologies. So the theory of the relativity has its starting point in what I still believe is probably the most amazing discovery in entire science. It is the so-called Michelson and Morley effect. So it is a long story how Michelson and Morley have done their experiment. Anyway, what they have found. So there is, in mechanics, we have this very simple law of the composition of the velocities. Let's assume that we are in a bus, and the bus is traveling with respect to the ground, and we are moving in the bus. So obviously our velocity with respect to the ground should be the velocity of the bus plus our velocity if we are moving in the same direction, or minus if we are moving in the opposite direction. So it is very obvious that if the light is emitted from the Earth, the light moves by its velocity, some velocity c, the Earth moves with some velocity v, so the velocity of the light should be c plus v or c minus v, depending on the direction it is emitted. Now, Michelson and Morley have found that, in fact, this is not the case for light. And the speed of light is the same in both directions.